Okay, so today we are going to start a very important theorem called the green theorem. Before I talk about the green theorem, I have to give a definition of a domain which is called simply connect. Okay, simply connect a domain means there's no hole in the middle. Okay, roughly speaking. Okay, so this is this domain is simply connected. And this one, okay, now let's say, this one is not simply connected. It's connected, but not simply connected. Okay. Yeah, connected means any 2 points, you can find the path, okay? But there's a hole here. So this is not simply connected. Roughly speaking, if you make a loop, okay? Here you see, if you make a loop, you can always shrink it without any obstruction. And this one, this loop, yes, you can shrink it to a point. But if the loop is around the, as a whole, you are not able to shrink the loop to that point. That's why it's not. That's why this kind of domain is not called simply connected. Okay. Okay. All right. So we Now the green theorem says that I have to talk about simple closed curve. That's a simple connector. Okay, a simple closed curve means it has an orientation. Okay, and let me state the theorem, and I try to explain to you all the conditions in the theorem. When you apply the theorem in mathematics, you have to know what is the assumption. Okay, so let C be positively oriented, okay, and the piecewise smooth, okay, and the simple closed in the plane. Okay, so and these domain increased by this curve C. Z is domain bounded by C. Okay, and then we have the following theorem. We also have to assume that PQ a continuous partial derivative, have a continuous partial derivative, okay? Then we have the line integral. This line integral, okay, P dx, Q dy is going to be changed to the double integral. That was a bigger discovery, okay? Yeah, okay. So where for any PQ which have a continuous partial derivative. Now, let me explain to you. Okay, what is a positive oriented? A curve is positively oriented. It go counterclockwise. Okay, it's closed. Okay, smooth means it may have some cusps here. Okay, but most of consists of several pieces. Could be like that square. This is a typical positively oriented piecewise simple closed curve. Okay, and something like that is also, yeah, this is a straight line, this is a semicircle. Those are the, yeah, simply closed means the domain it includes is simply connected, okay? So let's look at what the book says. Okay, yeah, the book does not say too much about this. Yeah, it's trying to, yeah, not just a simple closed curve referred to a simple counterclockwise transfer curve, okay? Well, this is required as a, okay, so the closed domain, the domain should be simply connected. Okay. Yeah, if the curve is oriented clockwise, then the line integral, yeah, you have to reverse the orientation. Okay, otherwise, you see here the C, the curve C is oriented counterclockwise. Okay, now if you are given a curve which is oriented clockwise, then if the above theorem does not hold, you have to change the sign. Okay, so the left hand side C, if you're told that the curve is counterclockwise, oriented counterclockwise, clockwise, then first of all you have to say this is a, you change the orientation, then you put a negative sign in front of that, then you will get a negative sign in front of the double integral. Okay, that's a remark. Okay, and there's a proof in the book. I'm not going to waste time to give a proof here. Okay, now what we can see here is, let's look at a special case. Okay, so as a corollary, okay, in English we say corollary means that implies, okay, if Q, the partial derivative was Q with respect to X is going to be the partial derivative of P with respect to Y. Remember that this condition is a necessary condition for the vector to be conservative. Okay, and when the domain is simply connect, then that is also become necessary condition. Okay, now a sufficient condition for vector field to be conservative. Okay, then this C px plus q dy, and that is going to be 0. Okay. Okay. All right. That implies. Okay, that implies two things. Okay, if you have two curves. Okay, so the line integral will be independent of a path, actually. So you can also show that. Okay, if this is a C1, that's a C2. Okay, and as long as they include the domain here, then you can also show that the integral of C1. Okay, C is going to be C1, the union of negative C1 is the union of C2. Okay, negative C1 means going in that direction. Okay, negative C1. So this domain is bounded by two curves. One is the C2, other one is negative C1 as a reversed with a reversed orientation. Okay, then the integral, okay, the integral of C p dx plus q dy is going to be 0, right? According to about theorem. So, but this integral will be negative C1 px plus C2 px dx pdx plus q dy. Okay, and this is going to be 0, and there's an assumption. So that would be negative C1 pdx plus q dy. So in other words, these two line integral are equal. Okay. So one can conclude that the line integral is independent of passes. Along a path is independent of path. Okay. Okay. So that means the vector field is a conservative. Okay. The vector field is conservative. Okay. Okay. So that means the vector field is a conservative. Okay. Anyway, so but the green theorem is true under the assumption the domain is simple. It's simply connected. Okay. Okay. So this also conclude that then the line integral, okay, this for any path not closed, okay, p dx q dy is independent of path. Okay, so that means that means equivalent to, okay, the vector field is conservative. That means f is going to be df for some gradient from f. Okay, for some f. Okay, so look, so under that assumption, you can also show that, right? You can show that this will be conservative. So let me state the fact. Okay, so if D is simply connected and FPQ, then FPQ is conservative, not N. Okay, then conservative if and only if Py equals Qx. Okay, so those two are equivalent. Okay, the difficult part is when PQ satisfies this equation, you have to prove that f is conservative, right? That means f can be written as a gradient of f, gradient of another function. So the idea is that you apply the green theorem, okay, and so the line integrals will be independent of the path, and the independent path, then you can define a function, little f, using an integral. Okay, remember this is how to define. Its definition is like that. It fixes a point, and this is a fix a point, and here's an arbitrary point, and draws a line, and there's no unique line there. Okay, curve. Then this will be the gradient. Okay, so it's f dr. Okay, this integral, because it's independent of the path. So maybe there's another path here. Doesn't matter. This independent path, and so this will be function of x, y. Okay, and that function is the one you want. Okay. Okay. Okay, that's the logic. All right, now, so let's take a look at some examples. Okay, here's the example first. Okay. So evaluate this integral c has xy dx x squared y cubed dy. Okay. Okay. And C is a triangle with vertices 0, 0, 1, 0, and 1, 2, with positive orientation. Okay. positive orientation means counterclockwise orientation, okay? So this is a triangle. And here's 1 and 2, and 1 and 0, and 0 and 0, okay? Now, if you try to solve this problem directly, okay, try to evaluate the line integral, then takes much longer time. You have 3 pieces. You have to evaluate the line integral along each side of the triangle. And you have to evaluate 3 integrals. That's too complicated. It's not like a circle, you know, it's easily you can parameterize it. It consists of 3 pieces. Okay. So by the green theorem, okay, one can get as double integral d. D is included by this, right? And remember, this is a partial derivative of qx, right? So if this is a q, that's a p, qx, p sub y, okay? Partial derivative dA. So let's calculate this. Q, partial derivative. So it's going to be 2xy cubed, okay? Right? The minus x. Yeah, because partial derivative p with respect to x is just with respect to y is x. So dA. Now you get double integral. Well, that double integral is easy to evaluate. Okay, so some of you may still have a trouble to set up an iterative integral for double integral. So watch out. Okay, you can. I'm going to show you 2 different double integral. If you want to start with x, then you look at the picture. X can be between 0 and 1. So lowest value for x is, smallest value for x is 0, the largest value for x is 1. Okay? Then you have to find for each x, you have to find the lower bound for the y variable, upper bound for the x variable, for the upper bound for the y variable. So clearly for the lower bound for the y variable along this vertical line, okay, it's going to be still 0, right? Now the trouble is the upper bound, but you can look at the equation of this line. The equation of this line is y equals 2x, okay? Y equals 2x. So the upper bound for y will be 2x for the fixed x. Okay. So that's the part. So it'll be 2xy cubed minus x. Okay. And you can evaluate this one by one, you know, right? The antiderivative of this with respect to y, maybe 1/2 of xy to the 4th power. Okay. This is antiderivative with respect to y. Let's evaluate the 2 endpoints. Okay, and then you plug 2x for x, for y, 2x for the y, 2x to the 4th power. Okay. Okay, 2 to the 4th power is a 16. 16 divided by 2 is going to be 8. 8 to the 5th minus 2x squared dx. Then find the antiderivative, which is 8 over 6 to the 6, and here 2 over 3x cubed. Okay. Okay, the final result will be 4 over 3 minus 2 over 3, which is 2 over 3. All right. Now you may also use a different way to, you can use a horizontal line to cut the triangle. So this double integral, I'm not going to evaluate, but I just said there's a different setting. Okay. So y is from 0. The upper bound for the y is 2. So y from 0 to 2, remember, okay? So that's dy. And for each fixed y, you look at the horizontal line. So now I have a point on this line. So what is the lower bound for x? What is the upper bound for x? Upper bound for x is 1. but lower bound for x should be expressed in terms of y, and which is because this line is y equals 2x, so x is going to be half of y, so that'd be half of y, and then you have x 2xy cubed minus x and dx. Okay, now if you write this, if you switch those two integrals and put half negative half y outside the integral, that you immediately tells me you don't understand iterative integral. Okay, so this is not equal to, if we express in that, I don't need to look at the rest of them. Okay, I don't need to look at the rest of them, and this is clearly it's wrong. Okay, we never, for iterative integral, we never had something like that. The integral outside the upper bound or the lower bound for the variable involves another variable. Never. Okay, you did not even think about how to set up iterative integral. Just put it there. So it's harder for me to give it any partial credits if I see the integral like that. Okay. All right. So this is yeah. If you use Green theorem, it'll be much easier. So here's another problem. Also, we can use the Green theorem and can quickly solve it. Okay. Without the Green theorem, it'd be challenging. I can show you. Yeah. So evaluate this integral. Okay. You will get y cubed dx minus x cubed dy. Okay. So what is the curve? The curve is a circle with radius 2. So x squared plus y squared equals 2 squared. It's oriented in that direction. Okay, that's a C. Okay. All right. So it's a closed curve. So it's very natural to apply Green theorem. And that's my P, that's Q. So it's double integral is going to be, right, Qx and Py. And then you will see Qx is negative 3x squared, Py, P sub y, right? It's partial derivative of P with respect to y. It's going to be 3y squared d, yeah, it's a dA, right? dA. Okay. So you take a negative 3 out. And this is a circle, double integral on the circle, over the domain disk. So the best way to solve this problem is polar coordinates. Okay. So x equals r cosine theta, y equals r sine theta. So r is r squared is x squared plus y squared. All right, I is between 2 and between 0 and 2, theta is between 0 and 2 pi. Okay, so this is my d prime, right? So I can put, I'm not in big hurry to write the iterative integral, but then I get r squared plus y squared is r squared, and here's another dA prime. Okay, because this is the integral over that rectangle. Okay, and r here is theta. Theta is 2 pi, I is from 0 to 2. That's the d. Okay, that's a d prime. So now you can use any of the order of the iterative integral. Okay, so it's going to be r cubed d theta dr. Okay, but this r cubed is independent of theta. That's why I got 2 pi. 2 pi times 3 is given 6 pi. Okay. So the antiderivative of r cubed is 1/4 of r to the 4th power. And finally, we get the answer. 2 to the 4th power. 2 to the 4th power divided by 4 is going to be just 4. Okay. So negative 24 pi. Okay. Now, if you do not use a green theorem. It will be difficult. It's complicated, okay? So this is again, let's look at y cubed dx. Okay. If you do not use green theorem to solve the problem, how do you do that? Well, you have to parameterize this curve. Okay. So t is from 0 and 2 pi. Okay. So you plug into this integral. It's from 0 to 2 pi. Y is going to be 2 sine t cubed, right? And the dx is going to be negative 2 sine t dt. Second one is, and the 2 cosine t cubed. dy is a 2 cosine t dt, okay? So you have the same dt now negative sign, so you can take a negative 4 out. Negative 2 to the 4th power out, okay? So then you get sine to the 4th power plus cosine to the 4th power, t and the dt. I'm not able to simplify sine to the 4th power plus cosine to the 4th power. So you have to find a way to evaluate this integral, okay? And I think it's possible, you know, okay? And actually those two integrals have the same value, okay? Sine to the 4th power, the integral from 0 to 2 pi is the same as the integral, yeah. The integral from of a cosine to the 4th power, okay? Okay, so let's look at, okay? Sine squared is going to be half of 1 minus cosine 2t, right? Cosine squared t is 1 plus cosine 2t. I hope you still remember this, okay? And okay, so it's not too bad when you square it. So you will square it, right? Square and square, right? Then you get, yeah, this is a sine to the 4th power t, okay? Then you get, you know, when 2 in the denominator taken out, so it'll be 2 square here, okay? And I have a 1 square plus cosine, 1 square plus cosine squared, cosine 2t squared. And here's another one, right? So if you can do the computation quickly, I get 2 plus 2 cosine squared 2t, okay? And the dt, okay? So actually you still get this, okay? Now, cosine squared 2t is going to be 1/2 of 1 plus cosine 4t here, okay? And you will get 3/2, right, plus 1/2 cosine 4t dt. But the integral of cosine 4t over the integral from 0 to 2 pi is going to be 0. Okay, you can always, you can quickly see that, get this result. But otherwise, just use the antiderivative. Okay, so the antiderivative, this is a t plus 1/8 sine 4t. And evaluate the endpoints. And so you get 3/2 and 2 pi. The second one is 0, okay? Because sine 4 times 2 pi is going to be 8 pi. Sine 8 pi is 0. Okay, so eventually you will get 24 pi, again, negative 24 pi. So some problems, either way is okay, then and a little bit more complicated. One of them, you know, you can evaluate the integral directly. Okay, you can evaluate the integral direct. So if we get a domain, if we get a curve which is closed, then it's always easy to evaluate the line integral using the Green theorem, converted to the double integral. Okay. But sometimes you can make a closed curve. Okay. For example, if I have a C here, and this is going to be x cubed dx plus y cubed dy. Okay. The curve is a parabola. Okay, 1 and 1. Okay. It's not a closed curve. C is a curve y equals x squared from this to this. Okay. But this is not a closed curve. You can do it in the following way. You can add another curve, C prime. Okay. So instead of, instead of C, let's say C, the union of these two curves, okay? Orientation is like that. Okay. This is going to be, okay, this is going to be, I think I have to make it a little bit complicated. I put X here, otherwise this is X, okay? So this is going to be two integrals. One is this. Okay, another one will be C prime. Okay. Okay. All right. All right, now this two curve includes a domain. So it's according to Green theorem, it's the integral of this double integral. So double integral is a partial derivative of x of the q, okay, minus this. Okay, so let's evaluate this integral first. So that is going to be yq. That's it, dA. And look at this is a special region, right? You can iterate integral, use a two iterate integral. X is from 0 to 1. And the y has a lower bound and x bound, upper bound. Okay. So this line is y equals x. This curve is y equals x squared. So it'll be x squared to x. And then y cubed and dy. Okay. So you will get the antiderivative here, evaluated to endpoints, x to the fifth minus x squared, and to the fourth power is x to the eighth. No, to fourth power, yeah. Okay, so dx. Then you find the antiderivative of this number. It's 5 of x to the fifth, 1 over 9th, x to the 9th. Okay, the final answer will be this. but this not the, this is just the integral, the double integral, right? Now look at this too. We don't want to parameterize this, but we can parameterize this, right? So this is going to be the integral. Okay. Now I can change the sign and the C double prime, right? Or the negative sign. Okay, what does it mean? That means this will be that direction. I change the orientation. Okay, it's easy to parameterize it. So for that one, you can x equals t, y equals t. The parameterization is very simple. Okay. So therefore, instead of using the parameterization for the parabola, I just use another path from that point to that point. Okay, so that's going to be from 0 to 1. X is a t, so tq. Dx is just dt. Here's y. That's t to the fourth power. Okay, so dt. Okay, then you find the antiderivative of this function. And you will get a quarter of t to the fourth power plus 1/5 t to the fifth power. Okay. The final answer is, let's rewrite this again. Because this example shows you can create a closed curve, but the other piece, it's easy to parameterize. Okay, then that's a quarter plus 1/5. Okay, so now this is identity, right? So now I can say that the above answer, I forgot, 1/4, 1/5 minus 1/9, and it moves that term to the other side. So that will be the answer. Okay, but usually people don't do that. It takes I just say it's possible you can do, in order to evaluate a line integral from this ugly line, right? Then you can make a simple line, a curve, so that you can translate the line integral along the C to the line integral along the C prime, for example. Okay, so so along the C prime, then C prime is easy to parameterize. Then you have the double integral. Okay, you have to evaluate double integral. Now, now how about the domain which are not simple? Okay, for non simply connected domain. Okay. Okay. Such as like that. Then the curve so the curve from this curve is not enough. C1, this is not enough to enclose the region because there's another hole inside. So we need when we say the region is enclosed by curve, another single piece, you cannot, you have to have the two pieces. It's a other orientation, that's a C2, okay? Then we said that those two curves are positive oriented, include and bound the domain D, okay? So this is this is what, if the domain is bounded by two curves, and those two curves must be, outside one must be oriented counterclockwise, the inside one be oriented clockwise, okay? Then then you can have then you have then you're given vector field like F is going to be P and Q here, right? Then this let's write the double integral another way. Okay, double integral first. So D, okay, Qx minus Py dA is going to be the line integral C1 C2 P dx plus Q dy. Okay, so yeah, you have a domain not simply connected, but consists of two closed curves. Okay, the inside curve, closed curve, actually the boundary of the whole. Okay, and outside curve actually includes the domain. Okay, then you have this too. You have this formula again. Okay. So more general, okay. So more general, if you have more than one host, right? Okay, more general. Okay, if there's more than one host, we can do the yeah. So if we have a domain here, okay, if the okay, so all sides must be oriented in this way, and then inside it's oriented in this way, C2 and C3. Okay. All right, so the boundary still consists of closed curves with orientation. Okay. Then we have then we have the following theorem again. Line integral to union of the three curves P dx plus Q dy. Okay. So now let's take a look at some examples. I want to see any examples in the book. All right, so here's the example. Okay, we're going to evaluate the integral c ky squared dx plus 3xy dy. Okay, and the c is right, c is a curve. It's like that. Let me describe it. Okay. Okay. So includes it's bounded in the region like this. Okay, semicircle, two semicircles. The outside one will be x squared plus y squared equals 2 squared. The inside one will be x squared plus y squared equals 1. It's oriented in this way. Okay. It's a closed curve. Now, this closed curve, and actually is a simple curve. That means the domain enclosed by this closed curve is simply connect. Okay, so this line integral by the Green theorem, you can apply the Green theorem. Okay, it will be the double integral. Okay, and such that 3xy x, right, partial derivative minus and dA. Okay, so you will get 3y minus 2y dA. Okay, so it's just the double integral of this. All right, so question is, how do you evaluate this double integral? Okay, the easiest way to do is use the polar coordinates. X equals r cosine theta, y equals r sine theta. Now the I is between 1 and 2, theta is between 0 and pi. Okay, that is my d prime. Okay, so it will be double integral d prime. Okay, and the y is going to be r sine theta, and d is d, right, a prime. Okay, so you can use any of the order of the integral. So from 0 to pi, and that's the theta. And from 1 to 2, r square sine theta dr. Okay, so now as the entire derivative is going to be 1/3 r cubed sine theta evaluated at from 1 to 2. Okay, so I will get 2 cubed minus 1 cubed, right? Sine theta d theta. Okay, that is going to be 8 minus 1, 7 over 3. Entire derivative of sine theta will be negative cosine theta. And evaluate the 2 end points, I will get 2. Okay, so pi over 3 times 2, that will be 14 over 3. Okay, 14 over 3 is the answer. All right, now the next problem, we probably use the more general Green theorem. Okay, we consider the vector field in the following form, and that is going to be negative y x squared plus y squared. Okay, and x here x squared plus y squared. Okay. But our curve, is there any closed curve is even not given, right? So we want to show that this line integral, right, is independent of simple closed curve containing the origin. Okay, any simple closed curve, positive oriented. Right, and this around the origin. How about like that? Okay, and that means I have another one here, and then there must be 2 are equal. Why this is true? Okay, what I'm gonna do is I just take an arbitrary closed curve. Okay, and then I take a tiny small circle. This is x squared plus y squared equal epsilon squared. Epsilon is very small, and counterclockwise oriented. This is a This is a yeah, clockwise oriented, counterclockwise. This is a C. That's my C, C prime. Okay, clockwise oriented. All right, and then I have a domain like that. Okay, so this is a D. By okay, by green theorem, the general is a green theorem, right? This still be the double integral of this. Okay, that would be qx minus py So what is my qx? Okay, partial derivative of our given one is x over x squared plus y squared minus, right? So let's do the calculation. We hope this is going to be 0. Otherwise, it depends on the shape of the closed curve. Okay, so we differentiate. I get x squared plus y squared and the square. The numerator will be 1 x squared plus y squared minus x times 2x. So that's going to be y squared minus x squared. Minus, okay, put the plus here. Okay, and similarly, you will get x squared minus y squared, okay, dA. So this is going to be canceled out. It's always equal to 0. It's always equal to 0. So what does that mean? That means this the line integral along these two curves is always equal to 0, but this is the sum of this line integral, right? Okay. Okay, the sum of a line integral. And then the other way is just tiny small circle. The tiny small circle, you can fix it. Then, and they can even evaluate. I'm pretty sure this is a number independent of R, okay? So tiny small integral, right? So dr. Okay, this is going to be 0, right? All right, so our integral is going to be negative of this small one and clockwise oriented. Okay. Okay, so f dot. Okay, and we can even evaluate this. Okay, you can choose x equals epsilon cosine theta. Okay. Okay. Then if you want to change the orientation, then this will be still the same circle. You can counterclockwise. Okay, f dot dr. Okay, and then for this one, for tiny small circle oriented in that way, x is going to be epsilon cosine t, y is going to be epsilon sine t. Okay, t is between 0 and 2 pi. Then we go back to our integral. It's from 0 to 2 pi. Now this is still go back to the derivative. Okay, so here's negative epsilon sine t. Okay, cosine t squared plus sine t squared. Okay, and the dx will be negative sine t. Okay, and then plus the second part is x. X is epsilon cosine t. And the dy is epsilon cosine t dt. Okay, so this is a whole part. Okay, I think I have an epsilon square here missing. Yeah, epsilon square missing. So epsilon square is going to be canceled out. Epsilon square is going to be canceled out. What you get is a numerator denominator both here sine squared t, cosine squared t. Here cosine squared t plus sine squared t. You have an epsilon square on the top, also epsilon square at the bottom, and the dt. So the answer is just an integral of 1. That's always equal to pi. Okay, that is always equal to pi. Okay, this is very interesting phenomena. So if you have a vector field, okay, it's going to be negative y x squared plus y squared, x squared plus y squared. How do you describe this vector field? It's not defined in the at the origin, and it's going to be like that at every point. Okay, this vector is tangent perpendicular to that. Okay, but this vector is getting shorter and shorter when the point is getting away from the origin. Okay, so it's getting shorter and shorter. Okay, then in yeah, so it's going around. So any curve, any closed curve C, this line integral is always equal to pi. Okay, it doesn't matter where it's located, as long as it contains the origin. Okay, around the circle. Yeah, this is it's interesting, you know, phenomena, right? That's what we did. We computed. Okay, so let's stop here and